friends, welcome to my channel Civil Smart. Today we are going to design a strip footing where the 4 columns are there and there is a beam, and we have to design a structure is supported on 4 columns, each having a size of 400 by 400, and center to center spacing between the column is 4 meter, right? Safe beam capacity is given is 150, and due to site conditions the width of the footing is restricted. This width is restricted and FCK is 20 and FI is 415. This type of footing is very complicated to design manually and through any software, but through this spreadsheet we will design it very quickly and through few clicks only, right? So we have to put our data in these pink cells only, right? So we will calculate the size of the footing firstly, then we will calculate the CG of the footing, that is X bar, and the projection L1 and L2 value. Net upward pressure will be calculated. Next step, the shear force diagram of this 4 columns C1, C2, C3, C4. Next is the point of zero shear force where the bending moment is maximum will be calculated. Next is the bending moment calculation and bending moment diagram will be shown here. Calculation point of contraflexure where the bending moments are 0. The point of contraflexure distance from the left hand and the right hand will be calculated by this. Next is the depth of the footing on the basis of bending moment criteria. We have already done for the strap beam footing for 2 columns. The area of steel reinforcement in the shorter direction, that is the main steel, will be calculated. Distribution steel will be calculated. This is the detailing we will find out. One way shear check will be done in next step. Next, after designing the footing, we will go for the design of the beam, because there is a beam and there is a concept that for the hogging bending moment, these are the hogging bending moment, the beam will act as a T-beam because of the footing slab is available at the bottom, which is a compression side, and for the sagging bending moment under the column it acts as a rectangular beam, right? So the T beam will be designed, the depth of the footing will be designed, the reinforcement for hogging bending moment. For these hogging, negative bending moment will be there between the C1, C2, C2, C3 and C4, C3, C4. The area of reinforcement will be calculated. Check for the tension reinforcement for the condition. Reinforcement for the hogging bending moment between the column C2, C3 will be calculated. This is the detailing of the beam. The reinforcement for the sagging bending moment under the column C3. This is the maximum, and if the column load is getting the maximum movement which is greater than the doubly reinforcement beam will be designed, and under the column C1 and C4 the reinforcement calculation, and finally the shear reinforcement, shear for the beam will be calculated. So let's start our problem by this spreadsheet. We have to choose our FCK is 20, FI is 415, and bearing capacity of the soil is given as 150, and B is 400, and D is also 400. The center to center distance between the column is 4 meter. You can choose according to your condition. Okay, width is restricted for 2 meter. Column loads according to your structure load coming from the structure load, you can choose according to your load condition. If we take, this is 700 kilonewton in our case. On column 2 this is 1100. On column 3 this is 1200, and on column 4 this is 800, right? So total load is calculated, addition of all these 3800 kilonewton. Sulfate, that is 10% of working load, is this much. The total working load is 4180. So ultimate load is this much, and finally required area of the footing is 27.87, and area by B is the length of the footing, 13.93. So we can take 14 meter as per our requirement. Then this is area of the foundation provided is this much, and this is okay. So this is the detailing we have calculated, and in this case CG of the footing, column load and CG of the footing coincide at a distance X bar. So X bar distance we have calculated from the center of the column C1. This is by this formula. This is 6.21, and projection L1 and L2 is calculated, because L1 plus X bar, this is L1 projection here and this is L2 projection here. L1 plus X bar is L by 2, this is 14, we have taken 14 of the length, L by 2, so L1 is 0.79 and L2 is by this formula. These blue colors are the formula, right? So 1.21 is the L2. Next we can see that the net upward pressure is calculated by this formula 135.71, and load per meter width W into B is 271. So this is, now the next is the shear force. Shear force is already been calculated by this spreadsheet. You can see shear force left of A, shear force right of A, and this has been shown here, right? So next is the point of zero force. Shear force is then calculated. This is X from point C2. From point C2, this is distance 2.21 is the zero shear force. Same is 2.16 is the zero shear force, and this is 1.74 zero shear force. So where the zero shear force is there, the bending moment will be maximum, right? Now the bending moment calculation has already been done. So this is our bending moment diagram, right? So now next is the point of zero contraflexure. The point of contraflexure is that where the bending moment is zero, right? These are the points where the bending moment is zero. So point of contraflexure between C1 and C2, there will be 2 points between C1 and C2. This is the point of contraflexure and this is the point of contraflexure. This has been already calculated as X is 0.97 from left hand and 4118 from the left hand. This is same between C2 and C3. These are the points and these are the distance has been calculated, right? And between C3 and C4, point of contraflexure is calculated from the right hand, this much. These are the bending moment diagram. Next, depth of the footing. So width of the strap beam is 400 mm, right? Because the column size is 400 mm, the maximum size will be taken as the width of the footing, right? Width of the beam. So length of the overhang portion B1 is 0.8. How this is calculated? If this is 2 meter, so 2 minus 0.4 divided by 2 is 0.8, right? So this is B1, and for this we will calculate the bending moment at the face of the column. This is 43.43 and factored bending moment is 65.14. So coefficient for 415 is 138, we all know that. So in this case D required is 153. So for shear consideration we have to go for the higher side. If we choose 200 mm, we can see for the one way shear check, so increase in depth is required. So we have to increase the depth. If we go for 300 for the shear consideration, we have to go at least 2.5 times, right? We will check, okay, shape in shear. So we have to choose 300 as effective depth. Clear cover we can go for 50 mm in case of the footing, and dia we can go for 20 mm. 360 is the overall depth, and 200 mm for the edge depth, because on the edge there is a reduction of the movement, so that we can reduce the depth. Now area of the steel along the main steel will be along the shorter direction, right? So the main steel PT is calculated. Area of steel, this is PT into B into D, 1640. Minimum area of steel is this much. If we choose 16 mm dia, see that the rules for spacing is this much. We have to choose the minimum spacing. This is 230 mm. 16 mm at the rate 230 mm along the shorter span, right? So if we go for the higher dia like 20 mm, then this much is the shorter span spacing. So in this case we can choose 16 mm, 230 mm center to center. For the distribution steel along the longer direction, you can see that minimum area of the steel is required. Rules for spacing is this much, and 16 mm, 230 mm center to center is required. So one way shear check is okay. You can see that the one way shear check, this is the beam, this is 14 meter is the length, right? This is B1 800 mm. So critical section will be at a distance D from the face of the column. So this one is W1, V is W into W is the stress into W1 into L. L is the length. This is the area we have to take. So 950 kilonewton. Factored shear force is this much. Tau V is VU upon L into D, 0.34. Or we can see that 0.29 is the reinforcement, percentage reinforcement. So 0.29 is between 0.25 and 0.5. You can choose from here, and from table 19 you can see that for M20 for 0.25 this is 0.36 we have to put, and for 50 is this 4.48. so 0.380 is interpolation, this is calculated, and 0.38 is greater than tau b, this is 0.34. so okay, and shape and shear. Now we have to design the beam. So strap beam, width of the beam is 400 mm, and there is a concept that for hogging bending moment the beam will act as a T-beam. We have to design it as a T-beam, right? And for the sagging bending moment and the column, it acts as a rectangular beam. This is the basic concept. So this is the bending moment diagram we have already calculated. These are the point of contraflexure, distance of point of contraflexure from the left hand. These are the values of the bending moment for which we have to design. So for the hogging bending moment, we can see that this is the maximum bending moment, 350 negative bending moment, and we have to calculate it as a T-beam. So B is the effective width we have to calculate by this formula, right? And distance between the point of zero movement, this is L0. Now distance between the point of zero movement L0 is 3.21. You can see that if we go for, this is the maximum bending moment C1 and C2, so distance is 4.18 minus 0.97, this is calculated as 3.21, right? So actual width of the footing B is 2 meter, width of the footing is 2 meter, actual width of the web is BW is strap beam, this is 0.4, and depth of the flange is 360. We have already calculated 360 is the depth, 400 mm is the width, and 2 meter is the actual width, right? So this has already been taken, and finally in this formula we get the effective width of the flange BF is 973, and actual width of the footing is B is 2000 mm. So finally we have to take the lesser of the from these two values. So 973 is the effective width of the flange. So for the T-beam, effective width has been calculated. So moment coefficient is 0.138. You can see that maximum hogging bending moment we have to design. So 350 kilonewton meter, it has already been taken. So for hogging bending moment, D required is 563, right? For this from this formula, and for maximum sagging bending moment, this is 485. This has been taken from the maximum value, right? So 485 is the maximum. For sagging bending moment, D required is 663. So we have to take the D average value is 613. So the beam width depth is 620 we can take, right? So D dash is 20 mm for the beam case, so 640 is the overall depth. So 640 is the overall depth. So now we have find the overall depth of the footing, effective depth of the footing. So we go for the reinforcement for the hogging moment. So area of reinforcement between columns C1 and C2. This is column C1 and C2. So column C1 C2, AST required is this much according to the movement, right? For the hogging bending moment, this is 350. So area AST required is this much. Flexure minimum reinforcement is this much, 1236, and minimum area of the steel is required is this much. So we have to take the maximum value. This is 1659. If we assume 20 mm dia, so 6 numbers of bars are required, right? So we can see that for the tension reinforcement, this condition M1 by V should plus L0 should be greater than LD. M1 formula is this much, so value of XU is calculated, M1 is calculated, V is calculated, that is the shear force at contraflexure, right? L0 value will be greater of these two, is already been calculated. Tau BD for M20 is 1.2. So if we go for 1.2, we will find this is okay because this value is greater than LD value, right? This 1523 is greater than 940. Now the area of reinforcement between C2 C3, the same formulas are there. The value is 1236. If we same 20 mm dia we choose, so 4 numbers are required. You can see that 4 numbers between C2 and C3, 6 numbers between C1 and C2. These 2 numbers are extra, we will provide in the next layer. 4 bars will be go throughout. Between C3 and C4, this is the same area of reinforcement required, same 20 mm dia, so 4 numbers are required. So we have designed for the negative moment, that is hogging bending moment. In the top steel we have designed. Now for the sagging bending moment, we have to choose under the area of reinforcement under C3. We can see that the maximum moment is 485 and the moment of resistance given by this formula 0.138 FCK BD square, this is 424. You can see that the moment is greater than the resistance required, so this is doubly reinforced beam. For the doubly reinforced beam, XU max by D for FE415, this is 0.48. You can see that XU max is 297. M2 is the difference between the total movement minus MU limiting, right, for which compression steel is required. So effective depth we can choose, D dash is 40 mm, we can choose 40 mm. So you can see that D dash by D value is 0.06, so it will fall between 0.05 and 1. This is the table, we have to choose the value. Tau C dash for 0.05 is 415, 0.05 is 355, right? So we have to put 355, and for 0.10 is 353. You can see that 354 is by interpolation we get, and this is 354 FSC, right? So for the tension steel AST1 and AST2 we have to calculate. This has already been calculated by this formula. We have already known all these values. MU limiting upon 0.87 Fy D minus 0.42 XU max. XU max is calculated, right? So we have to assume the bar dia. If we choose 20 mm dia, so 9 numbers are required, right, under C3. 9 numbers are required under C3, right? So assume bar dia for the compression steel, same. If we choose 20 mm, 1 number is required, but we have already provided 420, so we don't have to require more. Next, tension steel under column C2, this is singly reinforced because M max value is less than the MU limiting, that is moment of resistance. So this is the area of steel required. If we go choose 20 mm, right, you can choose according to your requirement. So 6 numbers are required under C2. So these are the values because maximum moment, sagging moment will be under C2 and C3, right? So we have to provide the excess steel in these under these column only, right? Under C3 and C4, if you choose 20 mm, there is 4 numbers are required. Under C1 and C4, this is already singly reinforced. If we go for the same 20 mm, so 4 numbers are required. So you can see that this is 9 numbers are required, there is 4 numbers are required, and 4 20 mm will go throughout. 2 extra will be under this C2 column and 5 numbers extra in C3 column. You can see the detailing also. This is section XX. If we cut from this point, you can see that you will see 6 number of 20 mm bar, 6 number 20 bar in the sagging moment, right? 4 above and 2, this is 6 number, and this is also 6 number of 20 mm bars. And this is section YY. You can see that if you cut from this, so 4 numbers of bar above and 9 numbers of bar in the sagging bending moment. So this is the detailing part, right? So for shear reinforcement, you can see that maximum shear force is 614, tau v is 2.477, AST required is maximum shear force is 614. You can see the shear force diagram. It will take the maximum shear force is 614, right? So it has already taken the maximum shear force. Tau v is calculated by this formula. AST support is maximum is 1884. PT required is 0.76, right? So we have to see that this is the 0.76, so it will lie between 0.75 and 1, right? For M20, you can see that for 0.75 this is 0.56, so you have to choose 0.56, and for 1 we have to choose 0.62, right? So this is the TOSI value 0.562, so shear bars are required. VUS is calculated by this formula 474. If we choose 10 mm dia bar and 4 leg stirrups, then you can see that provide 4 leg stirrup 10 mm bar at the rate 140 mm center to center. These are the formulas, you can see that. So shear force is also calculated. So we have designed the beam, we have designed the footing, and we have already designed the shear force calculation. So you can see that with few clicks we have designed this 4-column strip footing, which is having a beam, right? So it is very simple to design through this spreadsheet. You can change your data, you can change these pink cells, and you will find the different values of shear force, the bending moment diagram, point of contraflexure, the design reinforcement for the footing, one way shear check, design of the beam. You have to design the beam according to this concept, T-beam for the hogging bending moment, and as a rectangular beam for the sagging bending moment, right? So next is we have to find the depth of the beam, the hogging bending moment under column C2, C1, C2, then C2, C3, and C3, C4, right? We have 4 columns. And for the sagging bending moment, we have to design accordingly. If this is doubly reinforced beam, we have to find the reinforcement by this, and the detailing will be given. So friends, if you like this video, please subscribe the channel for more design videos, and if you want this Excel sheet, please mail me on my mail ID, WhatsApp me on the number given, right? Thanks for watching.